By default, a computer program is rigidly brittle. If it encounters a single unexpected variable, a missing file, an invalid input, its response is catastrophic failure. The Java virtual machine has no built-in intuition. It requires explicit architectural instructions to survive these abnormal conditions. Application stability faces two distinct threats: synchronous runtime errors, which stem from bad data, and asynchronous execution conflicts, which result from bad timing. Take a synchronous failure. Attempting a mathematical impossibility, like dividing by zero, halts execution. The application crashes. An asynchronous failure is timing. Two parallel commands modifying the exact same data node at the precise same microsecond corrupts the system. Building production-ready Java applications requires mastering two specific controls: exception handling to manage internal error states, and synchronization to govern concurrent operations. Without these controls, a program is a fragile script, incapable of surviving unpredictable real-world deployment. Exception handling does not fix a broken file or correct bad math. It is a routing mechanism designed to bypass a failure point safely, so the normal flow of the program continues. Developers isolate volatile code by placing it inside a designated safety boundary, known in Java as a try block. When an abnormal condition occurs within this boundary, the execution path diverts immediately. It skips the remaining instructions and routes into a designated recovery zone. This recovery zone is the catch block. It intercepts specific generated error objects, like an arithmetic exception, allowing the program to log the issue and recover smoothly. Whether the execution bypasses an error or completes flawlessly, both paths converge into a mandatory cleanup phase. This is the finally block. Its role is to execute essential teardown operations, closing database connections or open files, ensuring the system does not leak memory. The syntax of try, catch, and finally turns fatal system crashes into manageable, predictable detours within the application's logic. The Java compiler actively categorizes threats. It forces developers to acknowledge certain risks during the compile phase, long before the program ever runs. Java groups anomalies under throwable, splitting into exceptions for recovery and errors for system failures. Exceptions divide further. Checked exceptions are external risks the compiler forces you to handle. Unchecked exceptions are runtime flaws in internal logic. Developers manage these risks through control delegation. The throw keyword explicitly triggers an exception object, while throws in a method declaration passes the responsibility of handling it up the call stack. When built-in classes are insufficient, developers define custom exceptions to enforce specific business rules, like creating an invalid age exception for a restricted system. This strict taxonomy forces developers to architect defensive perimeters around unpredictable external resources, while holding them accountable for internal logic flaws. A perfectly safe, error-resistant program has limited utility if it cannot scale to handle high volume. Multithreading maximizes seek-you-lose realization by splitting tasks into lightweight subprocesses that run concurrently. It allows an application to download a file and play audio simultaneously. To spawn these lightweight subprocesses, Java requires specific architectural patterns. The older method extends the thread class directly. Because Java allows single inheritance, this prevents inheriting from other sources. The modern method implements the runnable interface, providing a distinct task block handed to an independent thread shell. Runnable supports better object-oriented design because it clearly separates the specific task logic from the underlying hardware execution mechanism. While multithreading shatters the bottleneck of linear execution time, it introduces the dangerous chaos of asynchronous timing. To manage this concurrent chaos, the Java virtual machine must meticulously track the exact state of every thread at any given microsecond. The thread lifecycle is a 5-state machine. A new thread enters the runnable queue, waiting for CPU time, then drops into the active running zone. If it requires a locked resource, it is forcefully paused into a blocked state. Once the task is complete, the thread moves to the terminated state, releasing its allocated memory back to the system. Understanding this lifecycle is critical. A single thread stuck indefinitely in the blocked state can silently freeze an entire enterprise application. The fatal flaw of multithreading is the race condition, a scenario where multiple threads access shared memory simultaneously. If two threads read a central counter at exactly the same microsecond and both increment it independently, they will overwrite the core data with the identical result. The data is permanently corrupted. Shared memory requires strict architectural checkpoints. Java provides the synchronized keyword, functioning as a mutual exclusion lock, ensuring only one thread can enter a critical section at a time. To maintain efficiency, threads use inter-thread communication. The wait method allows a thread to politely pause and release the lock if it needs missing data. Methods like notify and notify all act as signals. When a thread finishes, it broadcasts a wake-up call to waiting threads, coordinating operations. Synchronization is the necessary tax paid for the speed of multithreading. It intentionally creates micro-bottlenecks to guarantee total data integrity. Under heavy load, a high-performance Java application fundamentally relies on all of these complex systems operating smoothly in tandem. Exception handling acts as the system's shield, isolating volatile code and protecting the core logic from corrupted input and external hardware failures. Multithreading and synchronization function as the system's engine and brakes, safely scaling execution speed across the CPU while aggressively protecting memory integrity. These mechanisms are foundational tools for building state-aware architecture. A robust application is engineered with deliberate boundaries that gracefully orchestrate both the inevitability of failure and the chaos of concurrency. Ultimately, true system stability is defined by its architectural capacity to absorb pure chaos and just keep running.